directly past the decade. Astounding. Scientific. The community, rapid internet, expansion. A Haas word, permeated and of digital concept. Every communication once aspect familiar of people only technologies leads to daily technolo lives. Has. It is quite difficult to find any individual in a modem society that has not been touched by new communication technologies ranging from cellular phones to Bluetooth. This book examines the basic principles of communication by electric signals. Before modem times, messages were carried by runners, carrier pigeons, lights, and fires. These schemes were adequate for the distances and data rates of the age. In most parts of the world, these modes of communication have been superseded by electrical communication systems, which can transmit signals over much longer distances, even to distant planets and galaxies, and at the speed of light. Electrical communication is dependable and economical. Communication technologies improve productivity and energy conservation. Increasingly, business meetings are conducted through teleconferences, saving the time and energy formerly expended on travel. Ubiquitous communication allows real-time management and coordination of project participants from around the globe. Email is rapidly replacing the more costly and slower snail mails. E-commerce has also drastically reduced some costs and delays associated with marketing, while customers are also much better informed about new products and product information. Traditional media outlets such as television, radio, and newspapers have been rapidly evolving in the past few years to cope with, and better utilize, the new communication and networking technologies. The goal of this textbook is to provide the fundamental technical knowledge needed by next-generation communication engineers and technologists for designing even better communication systems of the future. 1. Commune IC80ION systems. Figure 1. 1 presents three typical communication systems: a wireline telephone, cellular phone connection, a TV broadcasting system, and a wireless computer network. Because of the numerous examples of communication systems in existence, it would be unwise to attempt to study the details of all kinds of communication systems in this book. Instead, the most efficient and effective way to learn about communication is by studying the major functional blocks common to practically all communication systems. This way, students are not with the exception of the Postal Service. Point 2 Introduction. Figure 1. 1. Some examples of communications systems: wireless computers, wireless access point, wireline network. Merely learning the operations of those existing systems they have studied. More importantly, they can acquire the basic knowledge needed to design and analyze new systems never encountered in a textbook. To begin, it is essential to establish a typical communication system model as shown in Fig. 1.2. The key components of a communication system are as follows. The source originates a message, such as a human voice, a television picture, an email message, or data. If the data is non-electric, e.g., human voice, email, text, television, video, it must be converted by an input transducer into an electric waveform referred to as the baseband signal or message signal through physical devices such as a microphone, a computer, keyboard, or a CCD camera. The transmitter modifies the baseband signal for efficient transmission. The transmitter may consist of one or more subsystems, an aid converter, an encoder, and a modulator. Similarly, the receiver may consist of a demodulator, a decoder, and a converter. Figure 1.2. Communication system. INPUT 1. Communication systems 3. SIGA L transmitted received. TRA I underscore 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 minus 1 T underscore RAR underscore N underscore SMIT TER underscore underscore SIG underscore NAL underscore underscore CHRNNEL signal R RECEIVER. Output. Signal output. Transducer. Distortion and noise. The channel is a medium of choice that can convey the electric signals at the transmitter output over a distance. A typical channel can be a pair of twisted copper wires, telephone and DSL, coaxial cable, television and internet, an optical fiber, or a radio link. Additionally, a channel can also be a point-to-point connection in a mesh of interconnected channels that form a communication network. The receiver reprocesses the signal received from the channel by reversing the signal. Modifications made at the transmitter and removing the distortions made by the channel. The receiver output is fed to the output transducer, which converts the electric signal to its original form, the message. The destination is the unit to which the message is communicated. A channel is a physical medium that behaves partly like a filter that generally attenuates the signal and distorts the transmitted waveforms. The signal attenuation increases with the length of the channel, varying from a few % for short distances to orders of magnitude in interplanetary communications. Signal waveforms are distorted because of physical phenomena such as frequency-dependent gains, multipath effects, and Doppler shift. 4. Example, a frequency-selective channel causes different amounts of attenuation and phase shift to different frequency components of the signal. A square pulse is rounded or spread out during transmission over a low-pass channel. These types of distortion, called linear distortion, can be partly corrected at the receiver by an equalizer with gain and phase characteristics complementary to those of the channel. Channels may also cause nonlinear distortion through attenuation that varies with the signal amplitude. Such distortions can also be partly corrected by a complementary equalizer at the receiver. Channel distortions, if known, can also be precompensated by transmitters by applying channel-dependent predistortions. In a practical environment, signals passing through communication channels not only experience channel distortions but also are corrupted along the path by undesirable interferences and disturbances lumped under the broad term noise. These interfering signals are random and are unpredictable from sources both external and internal. External noise includes interference signals transmitted on nearby channels, human-made noise generated by faulty contact switches of electrical equipment, automobile ignition radiation, fluorescent lights or natural noise from lightning, microwave ovens, and cell phone emissions, as well as electric storms and solar and intergalactic radiation. With proper care in system design, external noise can be minimized or even eliminated in some cases. Internal noise results from thermal motion of charged particles in conductors, random emission, and diffusion or recombination of charge carriers in electronic devices. Proper care can reduce the effect of internal noise but can never eliminate it. Noise is one of the underlying factors that limit the rate of telecommunications. Thus in practical communication systems, the channel distorts the signal, and noise accumulates along the path. Worse yet, the signal strength decreases while the noise level remains for introduction steady regardless of the distance from the transmitter. Thus, the signal quality is continuously worsening along the length of the channel. Amplification of the received signal to make up for the attenuation is to no avail because the noise will be amplified by the same proportion, and the quality remains, at best, unchanged. These are the key challenges that we must face in designing modem communication systems. 1.2 Analog and digital messages. Messages are digital or analog. Digital messages are ordered combinations of finite symbols or codewords. For example, printed English consists of 26 letters, 10 numbers, a space, and several punctuation marks. Thus, a text document written in English is a digital message constructed from the ASCII keyboard of 128 symbols. Human speech is also a digital message, because it is made up from a finite vocabulary in a language. Music notes are also digital, even though the music sound itself is analog. Similarly, a Morse-coded telegraph message is a digital message constructed from a set of only two symbols dash and dot. It is therefore a binary message, implying only two symbols. A digital message constructed with M symbols is called an M-ary message. Analog messages, on the other hand, are characterized by data whose values vary over a continuous range and are defined for a continuous range of time. For example, the temperature or the atmospheric pressure of a certain location over time can vary over a continuous range and can assume an uncountable, infinite number of possible values. A piece of music recorded by a pianist is also an analog signal. Similarly, a particular speech waveform has amplitudes that vary over a continuous range. Over a given time interval, an infinite number of possible different speech waveforms exist, in contrast to only a finite number of possible digital messages. 1.2 1. Noise immunity of digital signals. It is no secret to even a casual observer that every time one looks at the latest electronic communication products, newer and better digital technology is replacing the old analog technology. Within the past decade, cellular phones have completed their transformation from the first-generation analog amps to the current second-generation, e.g., GSM, CDMA, and third-generation, e.g., WCDMA, digital offspring. More visibly in every household, digital video technology (DVD) has made the analog VHS cassette systems almost obsolete. Digital television continues the digital assault on analog video technology by driving out the last analog holdout of color television. There is every reason to ask, why are digital technologies better? The answer has to do with both economics and quality. The case for economics is made by noting the ease of adopting versatile, powerful, and inexpensive high-speed digital microprocessors. But more importantly at the quality level, one prominent feature of digital communications is the enhanced immunity of digital signals to noise and interferences. Digital messages are transmitted as a finite set of electrical waveforms. In other words, a digital message is generated from a finite alphabet, while each character in the alphabet can be represented by one waveform or a sequential combination of such waveforms. For example, in sending messages via Morse code, a dash can be transmitted by an electrical pulse of amplitude A2 and a dot can be transmitted by a pulse of negative amplitude. Actually, amplification may further deteriorate the signal because of additional amplifier noise. Here we imply the information contained in the speech rather than its details such as the pronunciation of words and varying inflections, pitch, and emphasis. The speech signal from a microphone contains all these details and is therefore an analog signal, and its information content is more than 1,000 times greater than the information accessible from the written text of the same speech. Figure 1.3. A. Transmitted signal. B. Received distorted signal without noise. C. Received distorted signal with noise. D. Regenerated signal delayed. A2. A2 1.2 Analog and digital messages 5 _QJ IR1 NT V JQJIFL equals A B C D A2 Fig 1.3 In an M-array case, M distinct electrical pulses, or waveforms, are used. Each of the M pulses represents one of the M possible symbols. Once transmitted, the receiver must extract the message from a distorted and noisy signal at the channel output. Message extraction is often easier from digital signals than from analog signals because the digital decision must belong to the finite-sized alphabet. Consider a binary case. 2 symbols are encoded as rectangular pulses of amplitudes A2 and A2. The only decision at the receiver is to select between two possible pulses received. The fine details of the pulse shape are not an issue. A finite alphabet leads to noise and interference immunity. The receiver's decision can be made with reasonable certainty even if the pulses have suffered modest distortion and noise. Fig. 1.3. The digital message in Fig. 1.3a is distorted by the channel, as shown in Fig. 1.3b. Yet, if the distortion is not too large, we can recover the data without error because we need make only a simple binary decision: is the received pulse positive or negative? Figure 1.3c shows the same data with channel distortion and noise. Here again, the data can be recovered correctly as long as the distortion and the noise are within limits. In contrast, the waveform shape itself in an analog message carries the needed information, and even a slight distortion or interference in the waveform will show up in the received signal. Clearly, a digital communications system is more rugged than an analog communications system in the sense that it can better withstand noise and distortion, as long as they are within a limit. 1. 2. Viability of distortionless regenerative repeaters. One main reason for the superior quality of digital systems over analog ones is the viability of regenerative repeaters and network nodes in the former. Repeater stations are placed along the communication path of a digital system at distances short enough to ensure that noise and distortion remain within a limit. This allows pulse detection with high accuracy. At each repeater station, or network node, the incoming pulses are detected such that new, clean pulses are retransmitted to the next repeater station or node. This process prevents the accumulation of noise and distortion along the path by cleaning the pulses at regular repeater intervals. We can thus transmit messages over longer distances with greater accuracy. There has been widespread application of distortionless regeneration by repeaters in long-haul communication systems and by nodes in a large, possibly heterogeneous network. For analog systems, signals and noise within the same bandwidth cannot be separated. Repeaters in analog systems are basically filters plus amplifiers and are not regenerative. 6 Introduction. Figure 1.4. Analog to digital conversion of a signal. Thus, it is impossible to avoid in-band accumulation of noise and distortion along the path. As a result, the distortion and the noise interference can accumulate over the entire transmission path as a signal traverses through the network. To compound the problem, the signal is attenuated continuously over the transmission path. Thus, with increasing distance the signal becomes weaker, whereas the distortion and the noise accumulate more. Ultimately, the signal, overwhelmed by the distortion and noise, is buried beyond recognition. Amplification is of little help, since it enhances both the signal and the noise equally. Consequently, the distance over which an analog message can be successfully received is limited by the first transmitter. Power. Despite these limitations, analog communication was used widely and successfully in the past for short to medium-range communications. Nowadays, because of the advent of optical fiber communications and the dramatic cost reduction achieved in the fabrication of high-speed digital circuitry and digital storage devices, almost all new communications systems being installed are digital. But some old analog communication facilities are still in use, including those for AM and FM radio broadcasting. 1.2. 3 Analog to digital (AD) conversion. Despite the differences between analog and digital signals, a meeting ground exists between them: conversion of analog signals to digital signals, AD conversion. A key device in electronics, the analog to digital (AD) converter, enables digital communication systems to convey analog source signals such as audio and video. Generally, analog signals are continuous in time and in range, that is, they have values at every time instant, and their values can be anything within the range. On the other hand, digital signals exist only at discrete points of time, and they can take on only finite values. AD conversion can never be 100% accurate. Since, however, human perception does not require infinite accuracy, AD conversion can effectively capture necessary information from the analog source for digital signal transmission. 2 steps take place in AD conversion. A continuous time signal is first sampled into a discrete time signal, whose continuous amplitude is then quantized into a discrete level signal. First, the frequency spectrum of a signal indicates relative magnitudes of various frequency components. The sampling theorem, Chapter 6, states that if the highest frequency in the signal spectrum is B in Hertz, the signal can be reconstructed from its discrete samples, taken uniformly at a rate not less than 2 B samples per second. This means that to preserve the information from a continuous time signal, we need transmit only its samples. Fig. 1.4, L.2 Analog and digital messages 7. However, the sample values are still not digital because they lie in a continuous dynamic range. Here, the second step of quantization comes to rescue. Through quantization, each sample is approximated, or rounded off, to the nearest quantized level, as shown in Fig. 1.4. As human perception has only limited accuracy, quantization with sufficient granularity does not compromise the signal quality. If amplitudes of the message signal m(t) lie in the range MP, the quantizer partitions the signal range into L intervals. Each sample amplitude is approximated by the midpoint of the interval in which the sample value falls. Each sample is now represented by one of the L numbers. The information is thus digitized. Hence, after the 2 steps of sampling and quantizing, the analog to digital AD conversion is completed. The quantized signal is an approximation of the original one. We can improve the accuracy of the quantized signal to any desired level by increasing the number of levels L. For intelligibility of voice signals, for example, L equals 8 or 16 is sufficient. For commercial use, L equals 32 is a minimum, and for telephone communication, L equals 128 or 256 is commonly used. A typical distorted binary signal with noise acquired over the channel is shown in Fig. 1.3. If A is sufficiently large in comparison to typical noise amplitudes, the receiver can still correctly distinguish between the two pulses. The pulse amplitude is typically 5 to 10 times the RMS noise amplitude. For such a high signal-to-noise ratio (SNR), the probability of error at the receiver is less than 10 to 6, that is, on the average, the receiver will make fewer than one error per million pulses. The effect of random channel noise and distortion is thus practically eliminated. Hence, when analog signals are transmitted by digital means, some EITOR, or uncertainty, in the received signal can be caused by quantization, in addition to channel noise and interferences. By increasing L, we can reduce to any desired amount the uncertainty, or EJ-TOR, caused by quantization. At the same time, because of the use of regenerative repeaters, we can transmit signals over a much longer distance than would have been possible for the analog signal. As will be seen later in this text, the price for all these benefits of digital communication is paid in terms of increased processing complexity and bandwidth of transmission. 1.2.4 Pulse-coded Modulation-A digital representation. Once the AID conversion is over, the original analog message is represented by a sequence of samples, each of which takes on one of the L preset quantization levels. The transmission of this quantized sequence is the task of digital communication systems. For this reason, signal waveforms must be used to represent the quantized sample sequence in the transmission process. Similarly, a digital storage device also would need to represent the samples as signal waveforms. Pulse-coded modulation (PCM) is a very simple and yet common mechanism for this purpose. First, one information betreffers tune binary digit of G or 0. The idea of PCM is to represent each quantized sample by an ordered combination of two basic pulses, place T representing 1 and po T representing 0. Because each of the L possible sample values can be written as a bit string of length log2L, each sample can therefore also be mapped into a short pulse sequence that represents the binary sequence of bits. For example, if L equals 1/6, then each quantized level can be described uniquely by 4 bits. If we use two basic pulses, place T equals A2 and po T equals A2, a sequence of 4 such pulses gives 2 by 2 by 2 by 2 equals 16 distinct patterns, as shown in Fig. 1.5. We can assign one pattern to each of the 16 quantized values to be transmitted. Each quantized sample is now coded into a sequence of 4 binary pulses. This is the principle of PCM. Transmission, where signaling is carried out by means of only two basic pulses, or symbols. 8 Introduction. Figure 1.5. Example of PCM. Encoding. Digit binary equivalent pulse code waveform. 00000 lil UUI 10001 20010 30011 LLLLLLLL 11111 40100 50101 60110 70111 81000 2LLLLLLLLLLL 9 1001 10 10 10 1 1 1011 2 LLLLL 2 12 1100 1 3 1101 1 4 1110 E22 LLLL 1 5 1111 EL2 2. The binary case is of great practical importance because of its simplicity and ease of detection. Much of today's digital communication is binary. Although PCM was invented by P.M. Rainey in 1926 and rediscovered by A.H. Reeves in 1939, it was not until the early 1960s that the Bell system installed the first communication link using PCM for digital voice transmission. The cost and size of vacuum tube circuits were the chief impediments to the use of PCM in the early days before the discovery of semiconductor devices. It was the transistor that made PCM practicable. From all these discussions on PCM, we arrive at a rather interesting, and to a certain extent, not obvious, conclusion that every possible communication can be carried on with a minimum of two symbols. Thus, merely by using a proper sequence of a wink of the eye, one can convey any message, be it a conversation, a book, a movie, or an opera. Every possible detail, such as various shades of colors of the objects and tones of the voice, etc., that is reproducible on a movie screen or on the high-definition color television can be conveyed with no less accuracy, merely by winks of an eye. An intermediate case exists where we use four basic pulses, quaternary pulses, of amplitudes plus or minus A2 and plus or minus 3 A2. A sequence of two quaternary pulses can form 4 times 4 equals 16 distinct levels of values. Of course, to convey the information in a movie or a television program in real time, the winking would have to be at an inhumanely high speed. For example, the HD TV signal is represented by 19 million bits winks per second. 1. 3-channel effect, signal-to-noise ratio, and capacity 9. 1.3 channel effect, signal-to-noise ratio, and capacity. In designing communication systems, it is important to understand and analyze important factors such as the channel and signal characteristics, the relative noise strength, the maximum number of bits that can be sent over a channel per second, and, ultimately, the signal quality. 1. 3. 1 signal bandwidth and power. In a given digital communication system, the fundamental parameters and physical limitations that control the rate and quality are the channel bandwidth B and the signal power Ps. The precise and quantitative relationships will be discussed in later chapters. Here we shall demonstrate these relationships qualitatively. The bandwidth of a channel is the range of frequencies that it can transmit with reasonable fidelity. For example, if a channel can transmit with reasonable fidelity a signal whose frequency components vary from 0 Hz up to a maximum of 5000 Hz, 5 kHz, the channel bandwidth B is 5 kHz. Likewise, each signal also has a bandwidth that measures the maximum range of its frequency components. The faster a signal changes, the higher its maximum frequency is, and the larger its bandwidth is. Signals rich in content that changes quickly, such as those for battle scenes in a video, have larger bandwidth than signals that are dull and vary slowly, such as those for a daytime soap opera or a video of sleeping animals. A signal can be successfully sent over a channel if the channel bandwidth exceeds the signal bandwidth. To understand the role of B, consider the possibility of increasing the speed of information transmission by compressing the signal in time. Compressing a signal in time by a factor of 2 allows it to be transmitted in half the time, and the transmission speed rate doubles. Time compression by a factor of 2, however, causes the signal to wiggle twice as fast, implying that the frequencies of its components are doubled. Many people have had first-hand experience of this effect when playing a piece of audio tape twice as fast, making the voices of normal people sound like the high-pitched speech of cartoon characters. Now, to transmit this compressed signal without distortion, the channel bandwidth must also be doubled. Thus, the rate of information transmission that a channel can successfully carry is directly proportional to B. More generally, if a channel of bandwidth B can transmit n pulses per second, then to transmit knots pulses per second by means of the same technology, we need a channel of bandwidth kb. To reiterate, the number of pulses per second that can be transmitted over a channel is directly proportional to its bandwidth B. The signal power P.1 plays a dual role in information transmission. First, Ps is related to the quality of transmission. Increasing Ps strengthens the signal pulse and diminishes the effect of channel noise and interference. In fact, the quality of either analog or digital communication systems varies with the signal-to-noise ratio (SNR). In any event, a certain minimum SNR at the receiver is necessary for successful communication. Thus, a larger signal power Ps allows the system to maintain a minimum SNR over a longer distance, thereby enabling successful communication over a longer span. The second role of the signal power is less obvious, although equally important. From the information theory point of view, the channel bandwidth B and the signal power Ps are to some extent exchangeable, that is, to maintain a given rate and accuracy of information. transmission, we can trade Ps for B, and vice versa. Thus, one may use less B if one is willing 1.0 introduction to increase Ps, or one may reduce Ps if one is given bigger B. The rigorous proof of this will be provided in Chapter 13. In short, the two primary communication resources are the bandwidth and the transmitted power. In a given communication channel, one resource may be more valuable than the other, and the communication scheme should be designed accordingly. A typical telephone channel, for example, has a limited bandwidth, 3 kHz, but the power is less restrictive. On the other hand, in space vehicles, huge bandwidth is available but the power is severely limited. Hence, the communication solutions in the two cases are radically different. 1. 3.2 Channel capacity and data rate. Channel bandwidth limits the bandwidth of signals that can successfully pass through, whereas signal SNR at the receiver determines the recoverability of the transmitted signals. Higher SNR means that the transmitted signal pulse can use more signal levels, thereby carrying more bits. With each pulse transmission, higher bandwidth B also means that one can transmit more pulses, faster variation, over the channel. Hence, SNR and bandwidth B can both affect the underlying channel throughput, the peak throughput that can be reliably carried by a channel is defined as the channel capacity. One of the most commonly encountered channels is known as the additive white Gaussian noise Awgn channel. The Awgn channel model assumes no channel distortions except for the additive white Gaussian noise and its finite bandwidth B. This ideal model captures application cases with distortionless channels and provides a performance upper bound for more general distortive channels. The band-limited Awgn channel capacity was dramatically highlighted by Shannon's equation. C equals B log 2 1 plus SNR bit S 1.1. Here the channel capacity C is the upper bound on the rate of information transmission per second. In other words, C is the maximum number of bits that can be transmitted per second, with a probability of error arbitrarily close to 0, that is, the transmission is as accurate as one desires. The capacity only points out this possibility, however, it does not specify how it is to be realized. Moreover, it is impossible to transmit at a rate higher than this without incurring errors. Shannon's equation clearly brings out the limitation on the rate of communication imposed by B and SNR. If there is no noise on the channel, assuming SNR equals U, then the capacity C would be U, and communication rate could be arbitrarily high. We could then transmit any amount of information in the world over one noiseless channel. This can be readily verified. If noise were 0, there would be no uncertainty in the received pulse amplitude, and the receiver would be able to detect any pulse amplitude without error. The minimum pulse amplitude separation can be arbitrarily small, and for any given pulse, we have an infinite number of fine levels. Available. We can assign one level to every possible message. Because an infinite number of levels are available, it is possible to assign one level to any conceivable message. Cataloging. Such a code may not be practical, but that is beside the point. Rather, the point is that if the noise is zero, communication ceases to be a problem, at least theoretically. Implementation of such a scheme would be difficult because of the requirement of generation and detection of pulses of precise amplitudes. Such practical difficulties would then set a limit on the rate of communication. It should be remembered that Shannon's result, which represents the upper limit on the rate of communication over a channel, would be achievable only with a system of monstrous and impractical complexity, and with a time delay in reception approaching infinity. Practical systems operate at rates below the Shannon rate 0.1.4 modulation and detection 1.1. In conclusion, Shannon's capacity equation demonstrates qualitatively the basic role played by B and SNR in limiting the performance of a communication system. These two parameters then represent the ultimate limitation on the rate of communication. The possibility of resource exchange between these two basic parameters is also demonstrated by the Shannon equation. As a practical example of trading SNR for bandwidth B, consider the scenario in which we meet a soft-spoken man who speaks a little bit too fast for us to fully understand. This means that as listeners, our bandwidth B is too low and therefore, the capacity C is not high enough to accommodate the rapidly spoken sentences. However, if the man can speak louder, increasing power and hence the SNR, we are likely to understand him much better without changing anything else. This example illustrates the concept of resource exchange between SNR and B. Note, however, that this is not a one-to-one trade. Doubling the speaker volume allows the speaker to talk a little faster, but not twice as fast. This unequal trade effect is fully captured by Shannon's equation EQ 1, where doubling the SNR cannot always compensate the loss of B by 50%. 1.4 Modulation and detection. Analog signals generated by the message sources or digital signals generated through AID. Conversion of analog signals are often referred to as baseband signals because they typically are low pass in nature. Baseband signals may be directly transmitted over a suitable channel, e.g., telephone, fax. However, depending on the channel and signal frequency domain characteristics, baseband signals produced by various information sources are not always suitable for direct transmission over a given channel. When signal and channel frequency bands do not match exactly, channels cannot be moved. Hence, messages must be moved to the right channel frequency bandwidth. Message signals must therefore be further modified to facilitate transmission. In this conversion process, known as modulation, the baseband signal is used to modify, i.e., modulate, some parameter of a radio frequency RF carrier signal. A carrier is a sinusoid of high frequency. Through modulation, one of the carrier sinusoidal parameters such as amplitude, frequency, or phase is varied in proportion to the baseband signal Mt. Accordingly, we have amplitude modulation AM, frequency modulation FM, or phase modulation PM. Figure 1.6 shows a baseband signal Mt, and the corresponding AM and FM waveforms. In AM, the carrier amplitude varies in proportion to Mt, and in FM, the carrier frequency varies in proportion Mt. To reconstruct the baseband signal at the receiver, the modulated signal must pass through a reversal process called demodulation. As mentioned earlier, modulation is used to facilitate transmission. Some of the important reasons for modulation are given next. 1.4. Ease of radiation, transmission. For efficient radiation of electromagnetic energy, the radiating antenna should be on the order of a fraction or more of the wavelength of the driving signal. For many baseband signals, the wavelengths are too large for reasonable antenna dimensions. For example, the power in a speech signal is concentrated at frequencies in the range of 100 to 3000 Hz. The corresponding wavelength is 100 to 3000 km. This long wavelength would necessitate an impractically large antenna. Instead, by modulating a high-frequency carrier, we effectively translate the signal spectrum to the neighborhood of the carrier frequency that corresponds to a much smaller wavelength. For example, a 10 MHz carrier has a wavelength of only 30 meters, and its transmission can be achieved with an antenna size on the order of 3 meters. In this respect, modulation is like 1-2 introduction. Figure 1.6. Modulation. A carrier. B. Modulating baseband signal. C. Amplitude modulated wave. D. Frequency modulated wave. AAM AVVV FVAV AVAA AVVV AVAV AVAA AVVVV TVA LG A MT C B C D. Letting the baseband signal hitch a ride on a high-frequency sinusoid carrier. The carrier and the baseband signal may also be compared to a stone and a piece of paper. If we wish to throw a piece of paper, it cannot go too far by itself. But if it is wrapped around a stone, a carrier, it can be thrown over a longer distance. 1.4.2 Simultaneous transmission of multiple Signals multiplexing. Modulation also allows multiple signals to be transmitted at the same time in the same geographical area without direct mutual interference. This case in point is simply demonstrated by considering the output of multiple television stations carried by the same cable, or over the air, to people's television receivers. Without modulation, multiple video signals will all be interfering with one another because all baseband video signals effectively have the same Bandwidth. Thus, cable TV or broadcast TV without modulation would be limited to one station at a time in a given location, a highly wasteful protocol because the channel bandwidth is many times larger than that of the signal. One way to solve this problem is to use modulation. We can use various TV stations to modulate different carrier frequencies, thus translating each signal to a different frequency. 1.5 DIGITAL source coding and error correction code ING13. Range. If the various carriers are chosen sufficiently far apart in frequency, the spectra of the modulated signals, known as TV channels, will not overlap and thus will not interfere with each other. At the receiver TV set, a tunable bandpass filter can select the desired station or TV channel for viewing. This method of transmitting several signals simultaneously over non-overlapping frequency bands is known as frequency division multiplexing (FDM). A similar approach is also used in AM and FM radio broadcasting. Here the bandwidth of the channel is shared by various signals without any overlapping. Another method of multiplexing several signals is known as time division multiplexing (TDM). This method is suitable when a signal is in the form of a pulse train, as in PCM. When the pulses are made narrower, the spaces left between pulses a phone user signal are used for pulses from other signals. Thus, in effect, the transmission time is shared by a number of signals by interleaving the pulse trains of various signals in a specified order. At the receiver, the pulse trains corresponding to various signals are separated. 1.4.3 Demodulation. Once multiple modulated signals have arrived at the receiver, the desired signal must be detected and recovered into its original baseband form. Note that because of FDM, the first stage O for demodulator typically requires a tunable bandpass filter so that the receiver can select the modulated signal at a predetermined frequency band specified by the transmission station or channel. Once a particular modulated signal has been isolated, the demodulator will then need to convert the carrier variation of amplitude, frequency, or phase back into the baseband signal voltage. For the three basic modulation schemes of AM, FM, and PM, the corresponding demodulators must be designed such that the detector output voltage varies in proportion to the input modulated signals' amplitude, frequency, and phase, respectively. Once circuits with such response characteristics have been implemented, the demodulators can downconvert the modulated RF signals back into the baseband signals that represent the original source message, be it audio, video, or data. 1.5 Digital source coding and error correction coding. As stated earlier, SNR and bandwidth are two factors that determine the performance of a given communication. Unlike analog communication systems, digital systems often adopt aggressive measures to lower the source data rate and to fight against channel noise. In particular, source coding is applied to generate the fewest bits possible for a given message without sacrificing its Detection accuracy. On the other hand, to combat errors that arise from noise and interferences, redundancy needs to be introduced systematically at the transmitter, such that the receivers can rely on the redundancy to correct errors caused by channel distortion and noise. This process is known as error correction coding by the transmitter and decoding by the receiver. Source coding and error correction coding are two successive stages in a digital communication system that work in a see-saw battle. On one hand, the job of source coding is to remove as much redundancy from the message as possible to shorten the digital message sequence that requires transmission. Source coding aims to use as little bandwidth as possible, without considering channel noise and interference. On the other hand, error correction coding intentionally introduces redundancy intelligently, such that if errors occur upon detection, the redundancy can help correct the most likely errors. 14 Introduction. Randomness, redundancy, and source coding. To understand source coding, it is important to first discuss the role of randomness in communications. As noted earlier, channel noise is a major factor limiting communication performance. Because it is random and cannot be removed by prediction. On the other hand, randomness is also closely associated with the desired signals in communications. Indeed, randomness is the essence of communication. Randomness means unpredictability, or uncertainty, of a source message. If a source had no unpredictability, like a friend who always wants to repeat the same story on how I was abducted by an alien, then the information would be known beforehand and would contain no information. Similarly, if a person winks, it conveys some information in a given context. But if a person winks continuously with the regularity of a clock, the winks convey no information. In short, a predictable signal is not random and is fully redundant. Thus, a message contains information only if it is unpredictable. Higher predictability means higher redundancy and, consequently, less information. Conversely, more unpredictable or less likely random signals contain more information. Source coding reduces redundancy based on the predictability of the message source. The objective of source coding is to use codes that are as short as possible to represent the source signal. Shorter codes are more efficient because they require less time to transmit at a given data rate. Hence, source coding should remove signal redundancy while encoding and transmitting the unpredictable, random part of the signal. The more predictable messages contain more redundancy and require shorter codes, while messages that are less likely contain more information and should be encoded with longer codes. By assigning more likely messages with shorter source codes and less likely messages with longer source codes, one obtains more efficient source coding. Consider the Morse code, for example. In this code, various combinations of dashes and dots, code words, are assigned to each letter. To minimize transmission time, shorter code words are assigned to more frequently occurring, more probable letters, such as E, T, and A, and longer code words are assigned to rarely occurring, less probable letters, such as X, Q, and Z. Thus, on average, messages in English would tend to follow a known letter distribution, thereby leading to shorter code sequences that can be quickly transmitted. This explains why Morse code is a good source code. It will be shown in Chapter 1.3 that for digital signals, the overall transmission time is minimized if a message, or symbol, of probability p is assigned a code word with a length proportional to log 1 p. Hence, from an engineering point of view, the information of a message with probability p is proportional to log L p. This is known as entropy source coding. Error correction coding. Error correction coding also plays an important role in communication. While source coding removes redundancy, error correction codes add redundancy. The systematic introduction of redundancy supports reliable communication. Point 4 Because of redundancy, if certain bits are in error due to noise or interference, other related bits may help them recover, allowing us to decode a message accurately despite errors in the received signal. All languages are redundant. For example, English is about 50% redundant, that is, on the average, we may throw out half the letters or words without losing the meaning of a given message. This also means that in any English message, the speaker or the writer has free choice over half the letters or words. On the average, the remaining half is determined by the statistical mixture of the language. If all the redundancy of English were removed, it would take about half the time to transmit a telegram or telephone conversation. If an error occurred at the receiver, however, it would be rather difficult to make sense out of the received message. The redundancy in a message, therefore, plays a useful role in combating channel noises and interferences. Point 1.6 A brief historical review of modern telecommunications. 1.5. It may appear paradoxical that in source coding we would remove redundancy, only to add more redundancy at the subsequent error correction coding. To explain why this is sensible, consider the removal of all redundancy in English through source coding. This would shorten the message by 50% for bandwidth saving. However, for error correction, we may restore some systematic redundancy, except that this well-designed redundancy is only half as long as what was removed by source coding while still providing the same amount of error protection. It is therefore clear that a good combination of source coding and error correction coding can remove inefficient redundancy without sacrificing error correction. In fact, a very popular problem in this field is the persistent pursuit of joint source channel coding that can maximally remove signal redundancy without losing error correction. How redundancy can enable error correction can be seen with an example. To transmit samples with L equals 16 quantizing levels, we may use a group of 4 binary pulses, as shown in Fig. 1.5. In this coding scheme, no redundancy exists. If an error occurs in the reception of even one of the pulses, the receiver will produce a wrong value. Here we may use redundancy to eliminate the effect of possible errors caused by channel noise or imperfections. Thus, if we add to each code word one moripulse of such polarity as to make the number of positive pulses even, we have a code that can detect a single error in any place. Thus, to the code word 0001, we add a fifth pulse, of positive polarity, to make a new code word 00011. Now the number of positive pulses is 2 even. If a single error occurs in any position, this parity will be violated. The receiver knows that an error has been made and can request retransmission of the message. This is a very simple coding scheme. It can only detect an error, it cannot locate or correct it. Moreover, it cannot detect an even number of errors. By introducing more redundancy, it is possible not only to detect but also to correct errors. For example, for L equals 16, it can be shown that properly adding 3 pulses will not only detect but also correct a single error occurring at any location. Details on the subject of error-correcting codes will be discussed in Chapter 1.4. 1.6 A brief historical review of modern TELECOMMUNICATIONS. Telecommunications, literally, communications at a distance, are always critical to human society. Even in ancient times, governments and military units relied heavily on telecommunications to gather information and to issue orders. The first type was with messengers on foot or on horseback, but the need to convey a short message over a large distance, such as one warning a city of approaching raiders, led to the use of fire and smoke signals. Using signal mirrors to reflect sunlight, heliography, was another effective way of telecommunication. Its first recorded use was in ancient Greece. Signal mirrors were also mentioned in Marco Polo's account of his trip to the Far East. 1 These ancient visual communication technologies are, amazingly enough, digital. Fires and smoke in different configurations would form different codewords. On hills or mountains near Greek cities there were also special personnel for such communications, forming a chain of regenerative repeaters. In fact, fire and smoke signal platforms still dot the Great Wall of China. More interestingly, reflectors or lenses, equivalent to the amplifiers and antennas we use today, were used to directionally guide the light farther. Naturally, these early visual communications systems were very tedious to set up and could transmit only several bits of information per hour. A much faster visual communication system was developed just over 2 centuries ago. In 1793, Claude Chappe of France invented and performed a series of experiments on the concept of semaphore telegraph. His system was a series of signaling devices called semaphores, which were mounted on towers, typically spaced 16 10 kilometers apart. A semaphore looked like a large human figure with signal flags in both hands. A receiving semaphore operator would transcribe visually, often with the aid of a telescope, and then relay the message from his tower to the next, and so on. This visual telegraph became the government telecommunications system in France and spread to other countries, including the United States. The semaphore telegraph was eventually eclipsed by electric telegraphy. Today, only a few remaining streets and landmarks with the name Telegraph Hill remind us of the place of this system in history. Still, visual communications via Aldous lamps, ship flags, and heliographs remained an important part of maritime communications well into the 20th century. These early telecommunications systems are optical systems based on visual receivers. Thus, they can cover only line of sight distance, and human operators are required to decode the signals. An important event that changed the history of telecommunication occurred in 1820, when Hans Christian